Alright, time for another draft. Physics.com video presentation. So this will be, hopefully, not too long. Just going over the pre-lever experiment specifications or something to do with how we understand the experiment will take place. Now, it's kind of hard to draw a flat lever, but the idea would be is to have a stick, not too long, not too short. I mean, somewhere under a meter, I guess, but very light, and put some sort of nylon, bushing, bearing of some kind, very slick, and just have the lever so it can spin in this horizontal fashion. And the idea will be is to have energy hit one side and have mass on the other side and launch it and see what kind of velocities you get in terms of how efficient the lever is at conserving the momentum. So that's the theoretical argument, is about the conservation of momentum, because for kinetic energy theory to be correct, somehow the lever has to fail to conserve momentum. You can't conserve kinetic energy and conserve momentum if you're using masses that are not the same. If you change the mass and you transfer the energy, you have to kill one of the two theories. Okay, so just a fact. All right, so that's my vision of it. Okay, that spins somewhere above the ground on a very slick surface, and it's just a spinning stick on a fulcrum, a center bearing. Just a minute. All right, come back. So this is the lever in space, as light as possible. Might have to put some sort of devices on it to prevent objects from sliding in direction. So that's what these little sticks represent. And basically the idea is, ideally it'd be good if you can vary the positions just to match it. I would argue that there should be some initial test, that is, you put some energy in. I guess I'll draw that down here. To the lever itself, just to see how much energy it takes to move the lever. So unlike in gravity, where frankly you have a counterweight that sort of helps in this regard, the disadvantage of the horizontal lever is that you do actually have to move the lever. So it will take some energy when you crash into the lever just to spin the lever. And so you figure out how much you lose. And then the other simple test would be to first just do the experiment where you have the same mass going in as you have on the lever, and you're just trying to see whether you conserve the momentum, whether you can get the energy here to substantially, like 95% of it, to fly out this other side. And once you can accomplish that, then you can start doing the experiments with other masses and see how it goes. So I'm saying, for the idea of the way to put the energy in, is to use the pendulum, as it's a fairly reliable source of energy. That's probably not perfect. Okay. You can swing it back down and it'll come in with a fixed amount. It's pretty good that it does the 4 times the height, twice the velocity, so you can kind of guarantee certain velocities without having a detector. Now, unfortunately, I don't think he has timing gates. He only has the kind of the radar type velocity detector, and that's not going to work for small objects. So you have to rely on frame rates or something else as a backup. So it should be videoed in as well as possible and as from as many angles as possible. Now, I thought of a way to guarantee the heights, is to make sure you can make something of the exact right heights, and then you can just put the ball on top of it on the string and then just slide this out of the way, and you're pretty much guaranteeing your falling distance. And so that might work to create a reliable velocities in and such. So that's what this is a picture of. Okay, so that's all of that. Now, the theoretical arguments are numerous. So I just thought I'd mention, I'll check my list, but I was also thinking it'd be nice if we could film this with a strobe light, because then you could really guarantee, your frame rate. get a really good image of the incremental change, in a time-lapse photo that has a strobe to do the timing. Might be a good idea if you have one available, but if not, so I'll see what else is on my list. Alright, bouncing is on the list of things to worry about, and I'm sort of the opinion that if you do the experiment, if you have these distances just right, that there shouldn't be any bounce. So when you drop the thing in, you don't want the object here to hit and then some of its energy to bounce off because it didn't make the conversion. Say you have a 2 mass here, and so if this is matched, it shouldn't be a problem. And so the only thing you have to match is the weight of the lever. So the thing that might change is this distance. It won't be exactly 2 units of distance here and 1 unit of distance here from the fulcrum, because you have to compensate for the amount of energy to move the lever itself. So it might need to be adjusted a little bit in or a little bit out to prevent bouncing, because it will bounce if this side is too heavy and if this side is too light. This one can't, it's not going to match the acceleration to the deceleration. So the deceleration and acceleration have to be matched. And so bounce would be something to look for, I suppose. So you just keep moving this, adjusting it until you get as less bounce as possible. Once you have as less bounce as possible, that's a good match. That kind of thing. So I'll see what else. Alright, so the other part of that bounce argument is whether or not to put maybe some Velcro on it, and then you can have them make sure they stick. And it's as stated before, if you're going to, you have to have the lever in some sort of position to start with, and what the starting position should be is another issue. But if you start with it level, like say if you have the 1 mass out here, it'd be rational to have a stop so the ball can't slide this direction. It can only go this direction. And the same for something dropping in. You want to make sure it doesn't slide down the lever, so there should be a stop that prevents it from sliding down the lever. Now, how practical that is, the pendulum, it should be okay. The pendulum should be centered on the spot you're hitting the lever, and should be able to freely swing the rest of the way and shoot the other pendulum up, I would imagine. I can only imagine it so far. Alright, some things that are obvious. Obviously you should test both modes. So dropping the 10-ton train, getting converted into a 5-ton train, going twice the speed, and also a 5-ton train converting into a 10-ton train, going twice half the speed. So the conversion should go both ways. More experiments the better, that kind of thing. So the rest of the video, I guess I'll talk about this image here. So I was thinking about angular momentum and the fact that it technically is the same as regular momentum. I mean, there's no kinetic energy correlate to angular momentum. It just basically is the gear argument, and you're basically saying if I'm going to rotate a mass here, a half mass here, or a full mass here, okay, that those rotational momentums are the same. That if I make these 2 wheels, they will spin with the same speed, and they will contain the same, what you could call whacking energy. If I put a stick on there and I was to stop it from spinning, they would hit with the same force with a half mass rotating here or a full mass rotating here. The basic conventional theory, I'm pretty sure, is that those 2 things are equal. The angular momentum is the same in those 2 configurations. And so basically this is just a lever spinning. Okay, I mean, it's the same exact argument, frankly. And so I just would be curious to the theoretical explanation for how, if I spin the lever, if I cause it to spin, can I put the same energy in, and because I put the half mass out here, I put the full mass here, can I cause it to spin at a different rate? And I guess my argument was there's no theoretical reason that should happen. So if I put pressure in, cause this wheel to spin, it will rotate exactly the same. It'll rotate the same number of times. It'll rotate at the same speed, because this mass and this mass are essentially the same momentum is what they have created. And so you can't get any different numbers. You have to get the same numbers. And so in a sense, okay, angular momentum sort of proves the argument that these two things are seen as the same. Now this goes back to the theoretical argument I've been begging for, is the explanation of how, I can have a half mass out here and how I can destroy the momentum, in the sense that I put this in, this energy. This one obviously has to move twice the distance. It will oscillate that way. If I'll cause it to oscillate, it'll oscillate with twice the velocity here as in here. And frankly, how can I go from that oscillating circumstance to the actual, where I stop the lever and just let the object fly in space? I can't really prevent it from going twice the speed. It can't reduce its speed to 1.4. The velocity, I mean, it can't change its velocity once it's got the velocity. So it doesn't theoretically make any sense to me to say that it can oscillate with twice as much kinetic energy out here, but it can't release that energy. So I think those are difficult arguments. I mean, I haven't gotten anybody in 2 years to draw a lever and explain how the momentum is destroyed, that somehow the fulcrum knows that this isn't really the same weight as this, that somehow it knows that the half mass twice the distance, that's twice the distance by the way, is somehow not exactly the same weight on the stick as this weight, and that somehow it knows not to move it at twice the speed. So doesn't make any logical sense, but this, I didn't think of this idea that this is basically a lever in motion, and you're just saying you're sticking the object to it and it's got no choice. I mean, if I rolled this object with the half mass out here and the 2 mass here, they would roll at the same speed. They would collect momentum at the same speed. Because as far as the mechanism is concerned, this is the same circumstance. Both of them are just, you could just average out them and just figure out it's the same circumstance as far as the weight of the material, the mass moving. It's the same amount of mv, momentum, angular momentum. Alright, so maybe that's enough of a video. I don't know if there's much else until we know what you're going to decide on and how to create the energy in, and then cause the energy out. Now, Brozo did do it with a spring, which was an inner, you could have a spring on one side, but then it's testing 2 different objects. It's testing the lever and the spring. And you put the 2 mass on, you put the 1 mass on, you create a consistent amount of compression in the spring, and then you launch it. And his results were 19 and 11. All right, pretty close to a 2 to 1 relationship between the half mass and the full mass in terms of the velocities. So these are the velocity numbers, not the momentum numbers. So obviously the velocities this was half the velocity that this was. It sounds pretty close anyway. And so that we have as some piece of evidence. And it's an experiment, couldn't hurt to have it redone, with pendulums. But this did create some angular rotation. Obviously, if you're creating angular rotation, you want to that's the problem with rolling things, is you're creating a bunch of angular momentum, and you have to create it out of the energy you're using from the spring. So the spring has to produce not only the linear motion, but it also has to produce the angular rotation, the energy in the rotation. So ideally, if this was done with pendulums, with the spring, might be an interesting experiment. But again, springs are becoming suspect in terms of how they're capable of pushing things at different velocities. and whether there might be real limitations to how fast they can release energy. And that it's not springs aren't infinitely fast, so there clearly are limitations to, you can compress them at any speed, okay, to a value. All right, so I can go, I could take 6 years to compress a spring, but the trick is can I compress it fast? The faster I compress it, do I degrade the capacity of the spring to resist the compression, or does it compress in a form that's not even? And obviously there is a maximum speed at which the spring can expand. So obviously, as I put lighter and lighter things on the spring, there's a point where the spring can't go as fast as it needs to go to push the object as fast as you want it to go. So I can put something ultra light on the spring, and it won't get any useful energy out of the spring because it's not capable of being pushed fast enough to take more momentum out of the spring. So those are real limitations. Certainly it should be capable of keeping things within the boundaries of the tolerance of the devices we're using. And that's really what some of these arguments about, or it's about those tolerances. The variables, I guess you could argue, could be theoretically eliminated as being significant, but you have to do that. There has to be some engineering value to the idea that you're in the safe zone versus the unsafe, or where you're going to tend to get, where you're losing the reliability of your linear relationship because you've exceeded the tolerances. Anyway, I think that's enough. I'll think about it for a minute and then and such. Alright, so I just thought I would just bring this back to the beginning. The experiment that started this, essentially, this obsession with the kinetic energy argument, was a physics girl demonstration, where she combined a 5-ton train going 10 miles an hour into a standing still 5-ton train. Both objects moved off, and the argument was that it lost half its energy, half its kinetic energy, although it kept every bit of its momentum almost. And my brain said, no, that's fart. That doesn't work. Because you need momentum to make noise and to deform things. So she made the argument that somehow half the energy was lost to sounds and vibrations and sparks and denting things and all of that. And clearly you can't do that without using momentum. In a car crash, the momentum of the cars is consumed by the crushing metal. The crushing metal isn't some incidental thing. It has to be created by taking the momentum of the cars. And again, momentum, there's another argument to be made here, is that momentum, pushes things in directions. So whatever has the highest momentum will push a collision in its direction, where in the case of kinetic energy, it doesn't work, and that doesn't happen. The collision stays where the momentum says it is. It doesn't move with the extra energy of the kinetic energy. So these are all little bits. So the idea of this lever experiment was just to prove that you can make a 5-ton train going 10 miles an hour using the thing that's supposed to have half the energy, the 10-ton train going 5 miles an hour. If I can make a 5-ton train out of the 10-ton train going half the speed, then I have created free energy. And the whole point is we know free energy can't be that simple. That stepping on a lever can't be a source of free energy. So therefore it falsifies Leibniz's theory, and that's what this really is. It's Leibniz's theory. It should be called Leibniz's physics, Leibnizian physics. And so that's the point of doing the experiment, is basically to prove it makes free energy, and therefore prove obviously that doesn't happen. Okay. It's obviously not real energy. Okay. So Till the next time and such.